Hello, my name is Dr. Annette Taylor. I'm a lecturer in physical chemistry here at the University of Leeds, and I'm going to be addressing the question, describe the mechanisms of sn1 and sn2 reactions using tertiary butyl chloride and n-butyl chloride respectively. So an overall chemical reaction can take place via a series of steps. The kinetics of the reaction, the rates of changes of the chemical species involved, can give us an indication of how the process takes place on a molecular scale, i.e. the reaction mechanism. A classic example of this is the nucleophilic substitution reaction, which was investigated by Professor Ingold. So he was a professor of organic chemistry here at the university between 1924 and 1930. A nucleophilic substitution involves exchange of a nucleophile with a free pair of electrons and a leaving group X attached to this alkyl group R. So a nice example of this is the reaction of n-butyl chloride with hydroxide ions. So we can add this species to a solution of hydroxide ions and the exchange will take place, giving rise to the alcohol product, 1-butanol. The rate of this reaction depends on the concentration of the hydroxide ions as well as the concentration of the n-butyl chloride. And we also have the rate constant in there, K. What this implies about how the reaction takes place is that it involves a collision between hydroxide ions and n-butyl chloride. So a direct attack of the OH on this carbon and simultaneous leaving of the chloride, taking its electrons with it. Since this reaction involves the direct collision between these two species, we say it's a bimolecular process. And so it's a nucleophilic substitution involving two species. If we were to sketch an energy profile for this reaction, we would see that the energy increases as we form a transition state, a high energy transition state, with the OH partially bonded and the chloride partially bonded, and then decreases to the final product state. In contrast, if we were to use tertiary butyl chloride and reaction with OH, again we would form an alcohol product, but this time we would find that the reaction rate would not be dependent upon the hydroxide ions. So we can see that it depends on the tertiary butyl chloride concentration, and again we have a rate constant, but it's independent of OH. So how is this possible? Well, the reason is because the reaction actually takes place via two steps. In the first step, we have dissociation of our tertiary butyl chloride to give a cation and chloride ions. In the second step, our cation becomes susceptible to attack by OH, and this gives our final product. The first step is the slow step in this series, and since this has to form before we can form our final product for the reaction, we say that this is the rate determining step for the whole reaction. And so the reason why the reaction doesn't depend on the concentration of OH ions is because this first step is unimolecular. It just involves the tertiary butyl chloride. And so we can write that it's a nucleophilic substitution involving a single molecule. So if we were to sketch a reaction profile for the second mechanism, we would find that we had formation of an intermediate species, the carbocation, before formation of the final products. And this carbocation is a local energy minimum on the energy diagram. So what determines then whether you go via the sn1 channel or an sn2 channel, and indeed both might be present at the same time? Well, really it depends on the structure of the species. Obviously, when we have tertiary butyl chloride, this species is inhibited from attack by OH because of these bulky side groups. Additionally, the cation is actually stabilised by these alkyl side groups. So if we were to sketch our cation with our 3 side groups, these alkyl side groups have an electron donating effect, actually stabilising this positive charge, which makes it more energetically favourable than a primary carbocation with only one R group and only one stabilising force. So of course which step is rate determining also depends on the other species present, and you have to be very careful when assigning a rate determining step. It might be that this concentration is very, very small, in which case this step becomes really slow, and if it was slower than this step, it might even be rate determining. However, in reality, other processes can also take place as well. So if this concentration was really small, then in fact this would become susceptible to attack by water, and water would play the role of nucleophile in this reaction. So you have to design your experiment very carefully in order to use kinetic data to tell you something about the reaction mechanism that's taking place. And Professor Ingold and his colleagues actually had extensive experimental evidence that allowed them to convince chemists of the possibility of this sn1 reaction mechanism.